So yeah, we are discussing some ideas in terms of like how we can basically generate some kind of like the images from the Nobel view of the 3D the scenes. So the idea of the structure from the motion was basically reconstructing 3D scene from the multi-view images, but getting the 3D the shape as kind of the point cloud. So that was kind of the issue in terms of that. If we basically want to get some photorealistic images from the new view, it was not possible because the output was kind of a point cloud. So this is basically kind of the output that we want to get. So basically, we want to get some kind of results in terms of like we are really getting some kind of images that we are really seeing the whole objects or the scene as we are basically seeing in the real the physical the place from the kind of the new views that we never have basically observed some of the images from there. So how can we do these kind of things? For that, basically, we are going to leverage the prediction power of the neural net. So for that, basically, what we are going to do is that this is basically setup. Basically, we are having some kind of a set of the images. And from that, we want to basically get the images from the Nobel view. And for that, basically, we are assuming now the situation that we are not having any kind of some ground truth 3D shape. We only have a set of the images from the different views. And from that, we are going to get some kind of the 3D construction. And from that, we are also going to synthesize some kind of images from the Nobel view. And the problem setup that basically we discussed specifically is the case that we are making a neural net, which is taking the camera matrix as the input. And for that, we are basically rendering some kind of image from that view. And the loss function that we are going to use is basically measuring the difference between the rendered image and the ground truth the image that we have. So based on this, what we are going to do in the test time is that we are basically generating the images from some kind of the unobserved viewpoints. So that was kind of the neural net-based kind of framework that we are thinking of. So here the question is that how we are going to basically generate some kind of the 2D images. So instead of like making some kind of the random pipeline, some sort of the black box that we are just feeding the camera matrix and generating the 2D images, actually we are going to leverage the classical the graphics pipeline in terms of that we are reconstructing the 3D shape in some ways, and then rendering this 3D output into the 2D plane in a way that we are basically getting the 2D images. So this is basically kind of the idea that we are going to leverage some kind of the physical concept in terms of that we are really having the 3D the shape in the space and projecting this into the 2D plane in terms of like getting the images. And for that, we also discussed kind of like some different ideas for the rendering the pipelines. So those are also very classical ideas in the computer graphics. Like one was basically the rasterization, which is kind of the object-centric. So we are basically projecting each of the faces of the mesh, and then basically checking the depth to basically write the information for each of the pixel. What is the big question? There will be ground truth images from the unobserved viewpoint for the loss function. How is it going to be done for the unobserved views? So basically in the training time, we are basically going to check whether the rendered images that we are rendering using the neural net is basically the same with the image that we have for that image. In the test time, obviously, we don't have any kind of ground truth, right? So that's the very typical the neural net pipeline, right? For example, like in the cases of like some classification tasks that you already have done for the point cloud. So you are basically training the neural net with the input, the output, the pairs, right? For some of the 3D shapes, you have some information of the classes of the object. So you are training the neural net in a way that when you basically feed the point cloud as the input to the neural net and get the label, the class label of each of the point cloud, you want to basically match the output, the label from the input, and also the ground truth label, right? So you train the neural net with the loss function, like matching the predicted label and the ground truth label in a way that when you also feed some kind of the new shape that you did not use in the training, you can also get some kind of the class label. So that's basically what we did for some typical prediction task, like the classification or the segmentation for those things. And we are going to do the same thing in this case. But in this case, basically the input is the camera matrix and the output is the 2D image, right? And for some of the samples of the camera models, the camera matrix, actually we are having the ground truth images. So we are training the neural net in a way to basically match the predicted the 2D image and the ground truth the 2D image in a way that when you also basically feed the camera matrix, which was not used in the training, you can still get some kind of the realistic image. So that's basically what we are going to do. Does it make sense with the question? Yeah. So that's basically what we are going to do. So basically the question was like, for the unobserved the viewpoints, we don't have the ground truth images, then how we can measure the loss? Obviously for the unobserved the viewpoints, we don't have the ground truth. So we are basically trained the neural net with the input, the output pairs, with some samples of the input and the output the pairs in a way that for some kind of the new sample that we did not use in the training, we can still get some kind of the plausible the output from the input. So basically some kind of the prediction the task. So that's basically what we are going to do. And here the idea is that we are not going to make some kind of the random, some black box the neural net for that, but we are basically going to leverage the classical the graphics pipeline in a way that we are basically doing some kind of the 3D reconstruction and then doing some rendering the 3D the outputs to the 2D plane in a way that we can basically get the 2D image from the rendering the process. Basically leveraging some kind of physical concept, basically projecting some 3D thing into the 2D plane. Make sense? Do we assume stock from motion data is available? If not available, does it reduce accuracy? That's a good question. So here basically we are assuming that we have the camera the matrix information for the old images. So we can think that this is kind of the process that you can run after the stock from motion in terms of that you are having all the camera information for all each of the images. So basically, as we also discussed in the previous lecture, like if we have some multi-view images, and then based on from the the pixel-wise the correspondence, basically we can calculate the extrinsic the camera matrices for the images. So now we are assuming that all this the camera matrix information for each of the image is basically given. So based on that, we are basically going to train the neural net in a way that we are not only getting the 3D point cloud the outputs, but we can also render some kind of the realistic images from the arbitrary views. So that's the main point. And also one more thing that actually we are not gonna discuss for now is that from the structure from motion, actually we can get not only the camera the matrix for each of the images, but we can also get some kind of the sparse the 3D reconstruction, basically the point cloud, right? So we can consider actually leverage this kind of the sparse reconstruction as well in terms of to achieve some kind of the dense reconstruction. So that can be actually some kind of the additional, some useful information. So there are also lots of the ideas in terms of like how we're gonna leverage this kind of some sparse reconstruction, the kind of the outputs from the structure from motion. But we are not gonna discuss that for now, but we might basically get back to that point sometime later after the midterm week. Any other questions? No question. Cool. Yeah. So that's kind of thing. So for basically what we are discussing is that we are going to leverage some kind of the rendering the process in the graphics the pipeline. That is basically the process that we are projecting some 3D the shape into the 2D plane, to the image plane in a way that we can get some kind of the images. So for that, basically what we can do is that if we are reconstructing the 3D as kind of the 3D mesh, then that will be quite easy in terms of that we can directly use all the ideas of the rasterization or the ray casting in terms of getting the 2D images. But actually, we also discuss some kind of the problems, the limitations in terms like when you try to get the 3D as kind of the mesh, there are lots of issues for that, right? Do you remember what are basically the issues when we try to get this 3D mesh in this pipeline, basically deforming some kind of the template mesh? First question. Yeah, there are lots of kind of issues. The first issue for this kind of a pipeline, just like deforming some kind of a template mesh, was kind of that there's basically the limitation in terms of the topology, right? So we can only generate a 3D shape that has the same topology with the template shape. And also it's very, so basically it's very challenging to basically generate some kind of the, some arbitrary shape with some kind of the arbitrary topology. And also what we also briefly discussed last time is that the update through the gradient descent would be also very slow. In terms of that, we're gonna only basically be able to update the first intersection point of the ray and the 3D shape. So every pixel, we're shooting a ray into the 3D space, and we're gonna basically see the first intersection point of this 3D shape. And that's basically the point that we are giving the information for each of the pixel, right? So basically, if we use this kind of the idea, we only be able to basically update some kind of the visible area of the 3D shapes from each of the image. So that might be also quite slow in terms of basically making some kind of the changes for the 3D shapes. So there are also kind of limitations in terms of like getting the 3D mesh as kind of the final the output, as we also discussed in the first few lectures. And we also discussed that basically having some kind of the implicit representation is quite effective in terms of basically having some kind of the 3D shape with the arbitrary resolution and also the arbitrary topology with some basically way better kind of the results, also with some kind of the compact representation. So there are lots of kind of some advantages in terms of like having some implicit representation for the 3D reconstruction. Any questions? Yeah. But basically the problem might be is that if we reconstruct the 3D thing using some kind of the implicit representation, one of the issues might be is that, in the rendering, so basically how we can basically render, for example, like if we are getting a sine distance function as kind of the 3D representation, how we can basically render the implicit function into the 2D plane. Obviously, we can consider basically converting this implicit function into some kind of the mesh first, but we know that also that basically involves lots of kind of the process, right? So in the neural net training, if you get a implicit function every time in the gradient descent and convert this into some kind of a mesh and run the rendering, there might be really huge competition for every single step, right? So basically, we might basically want to directly render a implicit function into the 2D images. Then how can you apply the idea of the rasterization or the ray casting to basically get some kind of the 2D, render the 2D image from the implicit function? So that's basically the big problem, right? And do you have any ideas in terms of how we can render a implicit function into a 2D plane without basically doing any kind of conversion into a mesh? Yeah, basically we need to do something about like ray marching kind of things. But if we think about like doing some kind of ray casting, the problem would be basically how we find the intersection, the point, the first intersection point with the rays, right? So there was the answer about like marching cubes, but what I mentioned here is that we want to basically like render some the implicit function without basically converting this back to some kind of the mesh. Right? So if we want to basically directly render a implicit function into the image, the idea might be is that we are basically applying some ideas, the ray casting, right? Then the problem becomes like how we find the intersection point between the ray and the 3D shape. And the simple idea actually we can do in the case that when you have the sine distance function is basically using this idea of this peer tracing. So actually this is really old idea that was first introduced in the 1995. Basically that's the idea in terms of that. So basically for any kind of the point. So let's think about that we are basically having a kind of the ray starting from here. And at this point, we'll basically get the information about the sine distance, right? Basically, the sine distance is basically giving the information about like the distance to the closest, the kind of the point over the surface, right? Does it make sense? So for each of the point, if we basically like, retrieve the sine distance for each of the point, then basically this is giving the information about like the distance to the closest point over the surface. So which means that when you basically march through this ray, when you basically advance through the array with that amount of the distance that you basically retrieve, at this point, there should be no the obstacles, for this basically the amount of the basically the range of the distance, right? Because we know that the signed distance that we basically retrieve at this point is basically giving the information that there should be basically no any kind of the obstacles in this range. So what we can do is that we can basically repeat this process. For every the point, you can basically fetch the signed distance. And if the distance is basically 0, that means that you are already at the intersection point of the ray and the surface, right? If the signed distance is 0, that means that the point that you are having is the point over the surface. So you can stop the ray marching, right? So you're having some basically the some kind of the signed distance, which is not 0. Then you can advance through the merge with that amount of the distance. And you can just like repeat this process. So after you go this the distance at the position at here, you can also basically retrieve the signed distance. And if the distance is not 0, then you can also advance a little bit more along this way. So by repeating this process, at the end, you will be basically able to find some kind of intersection point, right? Does it make sense? How do you set the starting point projection in this peer tracking? Well, I mean, that would be basically the case that we are shooting the array. So as we also discussed in the previous lectures, there will be a case that we are having the camera center here. And then from the camera center, we are shooting the arrays through the image plane into the 3D shapes. But SDF doesn't contain any color information, so the rendering will just be more. So this basically the signed distance function is the case that just to find the kind of the intersection point, right? So obviously for the colors or some appearance information, we may need some another implicit the function for that. That's a good point. So here the question is that the signed distance function does not contain any color information. That's true. Actually, for some color or some kind of the appearance information, actually we need another some kind of the representation that can be another implicit function. So we're also getting, we're gonna also discuss that point. But for now, let's just think about basically how we're gonna basically find do some kind of ray casting in terms like finding the intersection the point. So for that, basically we can apply this kind of this peer tracing the idea in terms of like simply doing some kind of the iterative the ray marching with the distance that you are retrieving from the signed distance function. That makes sense. So this is like very classical the idea that we can try to apply into our neural net. So what we can do is that in the some kind of neural net training, we can consider like doing some kind of the 3D reconstruction as kind of the implicit representation. And for each of the image, then we can shoot a ray and do this kind of spear tracing in terms like finding the intersection, the point, and basically rendering all the 3D shape into the 2D plane, right? And then basically compare the rendered image with the ground truth image that we have, right? But if we apply this kind of like spear tracing, what would be the downside for this? Any thoughts in terms of the limitation like this idea? Yeah, as you can see, basically there will be lots of issues in terms of making this process as the differentiable the pipeline. So everything should be basically differentiable if you want to basically apply the gradient descent. So making this process like differentiable might be kind of like one of the issues. Actually, there are some kind of the tricks to make this process like differentiable. So there are lots of the ideas in terms of like making some differentiable, some ray casting kind of the ideas. But basically it involves some kind of some complication in terms of making it differentiable. But actually, the bigger problem is that it's quite computationally expensive in terms of that we basically need to iterate this process as many as possible. And actually, the problem is that we don't know how many times we will need to iterate this process, right? Basically, for any kind of the random shapes and the arbitrary arrays, we don't basically have any information about basically how many times that we will need to basically iterate this all the process to converge into the intersection the point. And as you can see, this might be kind of one of the worst example. That actually, it turns out that this is the ray that is basically not making any intersection with the shape. So at the end of the day, what we're going to see is that this ray is not making any intersection, basically. So we are shooting the ray into the empty space. But if we basically shoot a ray like this, then actually we're going to see lots of kind of some intermediate points. Because the sign distance function for each of the point here will be determined by the distance to the surface here, right? So we're gonna need to basically iterate this ray marching tree process the multiple times. And at the end, what we are seeing is that actually this ray does not have any kind of intersection point. So it would be very, obviously this is the worst case, but there can be this kind of very, lots of the cases that we are basically seeing some, lots of the inefficient kind of the process, like finding the intersection points. So there are lots of kind of issues with this peer tracing. Any questions on this? Yeah, so what people tried to do at the very beginning was basically utilizing this kind of the ideas in terms of like how we're gonna basically render some impulse function without any conversion into some kind of the 2D images, so that we can do this kind of the Nobel view identities based on the 3D reconstruction. But that is not the kind of the efficient in terms of that we need to basically apply this kind of the idea that involves lots of kind of the computation. So that was basically not very successful in terms of like having this kind of the lots of the some computation issues. One question here is that for rendering the impulse function, like, do we have to render the surface information? How about slicing volume and the silhouettes in the numerous random directions? How about slicing the volume and render silhouette? So how can you render the silhouette? The question was that, do you have to render the surface information? How about slicing the volume and render the silhouette in the numerous random diffractions? I'm not sure I got the idea of like this question, but basically what we are going to do is basically rendering the silhouette of the volume. That's the shape, the surface information. So yeah, so what we basically want to do is that basically we are basically have some kind of solid object, like some kind of bottle like this. And what we typically want to do is basically getting some kind of like projecting this 3D shape into the 2D plane in a way that we can basically get the surface information. So that's why we are finding the first intersection the point, because we are assuming that all the 3D volumes is are basically some solid, some kind of objects. That basically when you render the 3D models, that would be basically the case that we are finding the first intersection of the point of the ray to the 3D object in terms of like fetching some kind of the appearance information like the colors or the materials, all the things. So that's basically what we are going to do. And here, all the question is that like when you have some volume information, how we can basically get the surface information in terms of like getting the intersection the point. And if we represent everything into the implicit representation, that can be good in terms of getting some good quality of this 3D reconstruction, but the rendering becomes like much more complicated with lots of the computation. So that's all the issues. And interestingly, like what people try to do to resolve this issue is that while we know like all these 3D models that we are interested in is basically some kind of a solid object, actually we are going to consider all these 3D models as just kind of some kind of the volume, not just having some kind of solid kind of things, the volume like some air or some kind of smoke or some kind of fluid. So we are now assuming that the ray is just not intersecting at the first intersection the point, but we are assuming that the ray can just like pass through the volume like this, while making some kind of some sort of the interactions with some kind of the particles in the volume. So now we see that the volume is kind of a set of the particles, like we are having some kind of the fluid or some kind of smoke in terms of that. The ray can still basically pass through the inside of the 3D volume by just making some kind of the interactions with some kind of the particles in the volume. So this is kind of like interesting in terms of like that, we wanted to basically leverage some kind of the physical concept in terms of like some 3D rendering into the 2D images. So we are not making any kind of the random black box from taking the camera matrix as the input and making just images. We really want to do some kind of the 3D reconstruction and then rendering this back to the 2D images. So leverage some physical concept for that. But here, the kind of the interesting idea is that we want to basically relax the condition of the solid the object. We want to see all the 3D models as kind of some sort of the volume. So it's actually slightly like violating some kind of the physical constraint, right? We know that all the 3D models that we have, so kind of solid the objects, but basically we ignore the fact and they're just like seeing everything as kind of some sort of volume. So that's kind of the interesting, some kind of the direction that people basically exploring in the neural rendering literature. And actually, in terms of like rendering some kind of some volume, not the solid object, actually this idea of the volume rendering is not new. Actually, the volume rendering, the idea has been basically studied for more than, I guess, like the 3 decades. The first idea of the volume rendering was introduced in the 1984. So this was basically the first kind of results, like rendering some kind of a smoke like this. And the same idea has been basically studied for more than basically 2 or 3 decades to render some kind of the fluids and the smokes. And so basically we are going to leverage this kind of the volume rendering the idea in terms of like doing some kind of 3D construction, but still slightly basically violating some kind of the physical rules in terms of like doing some volume rendering, like the solid object rendering. So that's kind of the interesting aspects in the neural rendering. Any questions on this? Can you explain why the volume rendering violates the physical constraint? Because like we know that all the objects that we have are basically the object that we are interested in are basically some kind of solid object. So which means that the ray cannot pass through the volume, right? The ray will basically basically find the intersection point with the 3D object, the surface, and then it will be basically reflected over the surface, right? Basically, what typically we can assume is that for all the solid object, the ray, if you shoot a ray from the camera here, that the ray will be reflected over the surface. It's not passing through inside the object, right? But since it's basically not easy to basically find the intersection of the point over the surface, basically what we are going to do is that we're going to assume that the ray can basically pass through inside the volume, while making some kind of the interactions with all the kind of the particles in the 3D space. So this is not the kind of the ideal case that we want to basically consider. But basically this basically makes all the computation much easier. So that's basically why we want to basically break the rules of some kind of physical concept of the solid objects and consider all the 3D objects as kind of this kind of the volume, where basically the ray can basically pass through into that. Any questions on this? Make sense? Yeah, so this is quite kind of the interesting kind of things. So we want to somehow leverage some kind of the physical concept in terms like not making some kind of the random black box from the camera matrix from the 2D images. So in terms like doing some kind of 3D reconstruction, so it's kind of the leveraging some kind of the physical concept, right? But in terms of that, we are not basically making the solid object, but making some kind of the volumes, basically having some sort of the particles spread it over in the 3D space. That's kind of like breaking some kind of the physical rules. So like it's like halfway the idea of like there was some kind of the physical constraints, which was basically giving the best performance in terms like getting some kind of the 2D images. So that's basically the idea that we are going to discuss here. So for that, let's first see kind of the earlier version of like this idea, which is the work that is called the deep voxels, which is like relatively like the simpler the idea with the things that we're gonna discuss in the next slides. But the idea of the deep voxels is basically the same setup, that we are basically going to reconstruct a set of the 3D deep voxels from the multi-view images. And as I mentioned in the previous slides, this is the case that we are assuming that we are having all the camera information for each of the multi-view images. So you can consider that this is kind of the next step of the structure from motion, in terms of that we are already getting all the camera information for all the multi-view images, and doing some kind of 3D construction in a way that we can render these things into some kind of the novel view that we did not use in our training. And here the focus is not to get the accurate 3D construction, but actually basically get the accurate, the precise, the rendered images from the rendering the process. And for that, let's think about this kind of the pipeline. So you can see that this pipeline might look some kind of a little bit complicated, but actually it turns out that this is quite simple, the idea. So by the way, basically here, everything that we are seeing in all these slides is basically kind of the simplified the idea in terms of basically we are seeing the 1D to 2D the relations. So what we are actually going to do is basically like rendering the 3D things into the 2D, right? But you can think that we are now seeing a kind of a slice of the 3D volume into the 2D plane. So also each of the image is like now represented as the 1D, right? So you can think that this is kind of the case that we are seeing a slice of the 3D volume and also a slice of the 2D image into the 1D vector. Make sense? So now we are having that, each of the image here represented as the 1D vector here. And we're going to also have some kind of another D vector here and the another D vector here and like this, right? And then basically we want to reconstruct this kind of the voxels in the 3D space, which is now described as kind of the 2D the grid here. And what we are going to do is that we first want to basically accumulate some kind of the features that are basically obtained from each of the images. So what we are going to do is that for each of the image, we first basically extract some kind of the feature using the convolution of the neural net, and we want to basically accumulate all the basically the features of each of the 2D pixel into this 3D space. So basically what we do is that we are shooting a ray from the camera center into each of the pixel in the image in a way that basically we can propagate each of the feature in the pixel into the voxels in the 3D space. Makes sense? So you can shoot a ray from the camera center to each of the pixel. Then you're gonna see lots of kind of the voxels that are basically intersecting with this kind of the ray. So without basically finding any kind of like first intersection point for all the voxels, we are basically propagating the feature of each of the pixel that we have. And then we are basically accumulating all these kind of the image pictures into 3D space. And the accumulation is basically done by some kind of the recurrent neural net. But actually, you don't need to especially use the recurrent neural net. For using any kind of the neural net, you are basically fusing the features that are coming from the pixels in the different views. So in the previous slide, what you can see is that for those kind of the cases, yeah. So for those kind of cases, you're gonna have some kind of image here and shooting the rays like this. You're gonna also have another the image like this, and also shooting the rays here. And you're gonna also accumulate the features of each of the pixel into the voxels in the 3D space, right? And basically, the accumulation is basically done by some kind of the recurrent neural net or some kind of some other neural network. And you can basically repeat this process by basically getting some kind of the per pixel features for each of the images and propagating these features into the 3D space and accumulating them. So that's basically our 3D reconstruction process, right? So the 3D reconstruction is basically not getting any kind of the precise 3D information, but basically just like accumulating all the 2D information in the 3D space, but getting some kind of 3D information, right? But once we basically accumulate all the pixel features into the 3D space, what we can do is that we can now just project all the basically the accumulated the vectors in each of the voxels into some kind of arbitrary view. Make sense? So once we basically accumulate all the per pixel the features into the 3D voxels, now we can do the opposite. Now we are basically projecting, basically aggregating all this kind of the accumulated the feature information along the array to recalculate basically the features at each of the pixel. And we can do the same thing for some arbitrary view in the test time as well. And so if we have some kind of the encoder that basically gets some kind of the per pixel the features for each of the image, then we're gonna now need to get some kind of the decoder, right? From the per pixel the features, now we should be able to also get some kind of the per pixel the color information. From that, basically, we can get the finally rendered image, and we can compare this with the ground truth image that we have. Make sense? So this will be basically the case that we are having in the 2D space. We are having the image, and we are having the encoder. So we are basically having some kind of the features, right? The per pixel the features. And basically, you accumulate this into the 3D space by basically with some sort of the ray casting step, right? And you basically accumulate all the features in the 3D space. And in the rendering time, you do the reverse thing. So now you project all the features in the 3D space into some kind of the image of the feature vectors. Then you will need to also have some kind of the decoder, which is basically converting these the features back to the image again. And then you basically check whether the basically rendered image is the same with the ground truth image that we have. Make sense? Very simple, the idea, nothing complicated. So here the one quick thing is that basically how we're gonna accumulate, basically aggregate all the basically the pictures in the 3D voxels, right? So once we basically accumulate all the pictures in the 3D space, we also need to do the opposite, but now basically aggregating all the pictures along this array. And for that, basically we will need to do some kind of the pooling, right? So we can also consider like different ways of like pulling all the information. What sort of the pooling that we can use? Any ideas for this? I mean, yeah, I'm not asking any specific things. I mean, for this is like very typical the situation that we need to somehow pull the information, right? And there can be, we can try any kind of the typical the pooling idea, any kind of the functional, like, some kind of a max pooling, average pooling, sum pooling, multiple pooling, where we can make some kind of so another the recurrent neural net to basically aggregate all the information. Yeah, so there can be some multiple ways in terms like aggregating all the information, right? So like one simple way might be some kind of the average pooling, where we can make some kind of another neural net that can process some kind of some sequential data. But here basically what they propose to do is basically doing some kind of taking some kind of the weighted sum, sort of actually weighted average. And for that, basically, they are making another neural net, which is kind of like predicting the weight for each of some kind of the voxels in the 3D space. So when you shoot a ray, so for each of the kind of the voxels, where basically the ray is basically passing through, we are having some kind of small neural net, which is predicting some kind of the weight for each of the voxel in a way that we can do some kind of the weighted sum, weighted average of all the features. And the basic intuition behind like having this kind of the module is that we are basically somehow having this module in a way that we can get the sense of the visibility. So if we have some kind of the higher the weights like this, which means that this voxel is like more visible than the other voxels, right? So here, while we are basically using some kind of the idea of the volume rendering, we are still basically seeing that which basically the voxel is like more visible than the other the voxels, right? So we are just getting the sense of the kind of visibility by predicting the weights for each of the voxels. And then based on that, we are taking some kind of the weighted average for all the features. And we hope that this kind of the neural net that basically predict the visibility is basically giving you some kind of physical sense in terms like which the voxel is more visible than the other voxels. Makes sense? So that's the simple the idea, and it turns out that so that's basically thing like so we are basically having some single layer this weight composite neural net in terms of getting the visibility and taking some kind of the so weighted sum like this, and these are basically the output that we can get. So as you can see, actually the output looks quite good. So here the image on the right hand side is basically the image, which is the closest image from each of the view that we are having. So on the left-hand side, you are seeing the output images while basically changing the camera pose. So basically the rendered images. And the right-hand side, you are basically seeing the image in the training data set, which has the closest image in terms of the camera pose. Here the question is that by the position of the input and the output. Is this question or not? So input and output from the position to input. Yeah. When you basically send a message to me, please clearly write down in terms of whether it's the question or the answer for my question. Any pooling technique works? Yeah, I mean, you can try any pooling the techniques, but here the thing is that what they propose is that if you take this kind of the like weighted average with some kind of the neural net here, giving some kind of information with the visibility, that can basically provide the best performance. That was kind of the idea in terms of adding some slightly more some sort of the physical sense in terms of getting the visibility information. But you can also get into some problem of this. Does the weighted sum network have a huge advantage over the other deep learning architectures? Yeah, they say that actually this can basically provide some kind of the better results. So this is actually the comparison. Let me show this. This is the comparison with some kind of the simple sort of the averaging pooling here, the last column, and also the case that we're having some kind of the network like predicting the visibility. You can see that there is some kind of the difference in terms of the output. Obviously, the version with the neural network that predict the visibility is giving some slightly basically the better the outputs, right? And let me also show some kind of the results more here. Yeah, those are also kind of some results. So it's really impressive in terms of they can also really reconstruct all the fine details here, right? Let me briefly show the video here.
We propose deep voxels, a persistent object-specific embedding to enable 3D reasoning in generative models. Deep voxels embeds both appearance and geometry for high-quality novel view synthesis.
So somehow the video is not played on my side. So yeah, let's skip the video. So yeah, basically this is the whole idea. So what we are going to do is that here basically we are just getting some kind of the latent features for each of the images and accumulating all this information into the 3D voxels, and then projecting this information back to the 2D images in a way to basically recover the images as well. And here the one of the key idea was basically having some kind of the reasoning about the occlusion in terms of basically predicting the visibility using a simple neural net. But that also has some kind of limitations. But basically, can you see also the limitations of like this work? What would be some kind of the downsides for this work? Visibility is not radiance. We did not discuss anything about the radiance. Visibility is really like how much the voxel in this 3D space is visible from the camera pose that we see. Yeah, as you can see, this is quite the memory heavy idea because we are having the 3D voxel representation, right? And also the downside would be is that we can also change the resolution. So we are basically, having all the same kind of the limitations of the 3D voxel representation, right? And also, while this work says that like having the occlusion, the aware, the projection is good in terms of like getting some kind of the better results. This one is also not have some kind of issues in terms of like it's not exactly it can be basically physically incorrect. What would be kind of situation that we are seeing some kind of the physically incorrect the outputs? Can you guess? I mean, think about the process that we are just predicting the visibility for each of the voxels. So while we do some kind of the volume rendering, actually the object that we are getting is kind of a solid object. So which means that what we can assume that if we shoot a ray, basically if this voxel is not visible, then obviously all the other voxels after this voxel should not be visible, right? So that's kind of the point. So while we basically do some kind of the volume rendering, the output that we're gonna get would be kind of the solely the object. And then the output that we want to see is basically the case that basically when you shoot a ray, if we see that this voxel is not visible, then we want to basically add some kind of constraint that all the voxels after this voxel should not be visible, even for the volume case, right? But here, in the case that we're just like predicting the visibility for each of the voxel independently, actually there can be some of the cases that the close to the voxel is not visible, basically having the lower the visibility score, while the voxels behind the voxel has the higher the visibility, which does not make sense. Is it clear? So there should be kind of the dependencies in terms of the visibility for the voxels in terms of that if the closer voxel is not visible, having basically the lower the visibility score, then obviously the voxels behind this voxel should have the same or even lower the visibility scores, right? So that's kind of the problem. So we are basically not having this kind of the basically no way to basically guarantee this kind of like to satisfy this kind of the some physical constraint in this kind of the pipeline. So actually, this is the case that we are not basically using the idea of the volume rendering that properly in terms of like not satisfying this kind of some physical constraint. So that's basically why we basically need to consider some kind of the upgrade version. So for that, now we are going to move on to kind of the some better the model, which is the famous the neural rendering. So let's move on to the NERF. So basically, NERF is basically solving these kind of issues for many kind of issues in the previous kind of the work in terms of making some three major changes. So as we have seen, one of the kind of limitation of the deep voxels is the case that we are using the voxel representation, right? And we want to basically have some kind of the implicit function as the final the outputs. So that's basically one major change that we are going to make. And the second basically the change that we are going to make is basically replacing the occlusion, the aware, the projection with some kind of the classical the volume rendering the equation that basically satisfies all the physical the constraints that we're gonna see. And one more the major change that we are going to make is basically not just using some latent features, but actually we are going to use some kind of some physically explainable quantity, which is the view dependent colors, and also some kind of geometric constraint as well. So actually, yeah, this is basically the outputs that we can see using the NERF. Yeah. So as you can see, basically the quality of the rendering looks quite good, right? So how we can basically achieve this kind of output? So as I said, like now we are not gonna basically use any kind of some latent picture. Sorry, somehow my slide is quite slow. But somehow we are going to get some kind of the view dependent color information. So you can basically think that the radiance that we call here is kind of the view dependent color information. So if you take the compare graphics course, you're gonna get some more the precise meaning of the radiance. Before that, so the question is like, what is the latent features? Well, basically, we are getting some kind of some feature vectors for each of the pixel that can be used for some kind of encoding and decoding. So you already implemented the autoencoder in our first assignment, right? Which was basically the case that we are basically mapping the entire shape into a kind of the latent code and decoding back to the 3D shape, right? So that was the case that we are basically mapping the full 3D shape into a kind of a latent feature. So that can be decoded into the 3D shape as well, right? And here what we do is that now we are basically encoding each of the pixel of the image into some kind of a latent code so that we can accumulate all the information in the 3D space. And then after we also project this back to the latent code, now we are also decoding this back to the color in a way that we are doing some kind of the extracting some kind of the image information into some kind of latent code. So the problem, like the good thing with the latent code is that the neural net basically like transform all the information in a way that the neural net can basically better basically interpret in some kind of the training process. But the downside of the latent feature is that we don't know what the meaning of the latent the code is, right? We're gonna get some kind of randomly latent some kind of the some information, random the numbers into the latent vectors, which will be basically encoded and decoded using the neural net. So the neural net can only know the meaning of each of the latent vectors. So here, instead of like having some kind of the latent vectors, we are going to basically directly get the color information and also some kind of the density, the geometry information. So which is basically more sort of the intuitive, explainable the quantity that we can also see understand the meaning of each of the information. And here the one thing is that we are not just getting the color information per point, but actually we are getting the information of the view dependent color, which means that for each of the point in the 3D space, for each point of the 3D space, we are getting the color information for each of the view direction, which means that depending on like from which direction we see the same point, the color of that point will be varying. So that's kind of the important point. And the reason why we are getting the view dependent color information is that basically we want to consider the lighting the information. So yeah. So basically we don't have any kind of information for the lighting the situation in the scene where basically we want to reconstruct the 3D objects. But as you can see in this kind of images, depending on like what sort of the lighting condition that we have, depending on the view direction that we are seeing the object, we're gonna see some kind of the changes of the color, right? So for example, for all this kind of sphere that has kind of the same color over the entire the surface, depending on the lighting and the view direction, the color for each of the point will be varying. So that's why basically we want to get some kind of the view dependent color information. Actually, the other way around that we can do the same thing is that we really reconstruct the lighting information as well. And they basically calculate the color for each of the pixel based on the lighting information and some kind of the reflection properties at each of the point. For example, like if we have some kind of specular reflection materials, that will be the case that the light is basically reflected along the incident direction and outgoing direction like this. But for some of the other cases, we are having some kind of the diffuse materials, basically where the light is basically distributed into some kind of all the random directions. We can see this kind of results, which means that basically if we can reconstruct all the light information and also the material properties, based on that, we can calculate the view-dependent color information for each of the outgoing view directions. But in the case that when we do not want to basically reconstruct the light information, we are basically directly getting the view-dependent color information in a way that we can basically consider the lighting condition without basically getting the exact lighting information. So that's basically what we are going to do. Make sense? Any questions on this? So what we are going to do is that basically we are making the two implicit function. As someone also asked in the Zoom chat, we are now getting the one implicit function, which is for the geometry, which is basically somehow representing some kind of the density map with the 3D sheets. We're going to also get into the exact meaning of this density map in the later these slides. We are also having another neural network, which is basically becoming the implicit function for the view-dependent color, which is the radiance. So for the radiance deep function, the input is both the 3D location and also the view direction, which is represented as the 2D angle. So by just taking the 5-dimensional D vector, basically having the X, Y, Z coordinates and the view direction, we are getting the color information. That's the implicit function for the radiance. And then we are having another implicit function, which is only taking the X, Y, Z coordinates and getting some kind of the density information. Make sense? And the next slide is the kind of the most important parts in the neural rendering. So this is basically the volume rendering the equation. So which is physically making more sense than the previously some kind of accumulation, the projection, the idea. So basically here, what we are going to do is that based on the two implicit functions that we have, so as we have seen, the first one was basically the density function, and the second one was basically the radiance function, right? Based on this, what we are going to do is that when you shoot a ray from the camera center into the 3D space, by sampling some of the lots of the points along this kind of ray, we're gonna basically calculate the final color value by accumulating all the information for each of the ray. So this is basically equation in terms of how we can calculate the color of each of the ray when you basically accumulate all the information of the samples along the ray. And what we are going to do is that basically what we can see, what's the question? So basically when you send me the direct message, so there should be two accounts of mine, one is from my iPad. So please find the other account because I cannot see the chat on my iPad side. Can you send me the question again? Shouldn't the ray reflect when it makes the reflected surface? Well, as I said, here the whole point is that we are seeing all the objects as kind of the volume, where basically we are not basically making any kind of reflection. We are assuming that the ray is passing through the volume. And the reason for that is basically very hard to basically compute the intersection point. And even when we are able to basically compute the intersection point, as we also have seen the mesh case as well, the update will be very slow because we are only updating a single point there. But as you can see in this case, we are updating through all the points along the ray. So this can basically make some much faster the convergence in terms of getting this 3D construction. So basically by breaking some kind of the physical constraints, actually we are basically making way faster the convergence and also the better results at the end with the neural net training. So that's kind of the interesting aspect in terms how much we're gonna basically leverage some kind of some physical constraints, or how much we're gonna also basically break some kind of the physical rules in terms getting the best results. So here, basically, what we are going to do is that we are seeing all the 3D objects as kind of some volumes where the ray can basically pass through inside the volume in a way that we can basically avoid the competition, like finding the intersection, the point. So that's basically the basic idea. Would there be any point of the ray tracing through a solid since they shouldn't be rendered at all? I'm not sure whether you understood my, yeah. And so, yeah, I think the question that about like any point over the ray tracing through a solid, since it shouldn't be rendered at all. I couldn't get what you mean. So basically, yeah, the whole point is that we are doing some kind of leveraging the idea of the volume rendering, where we are assuming that ray can pass through inside the volume, so that we can get some kind of the avoid the competition of the like finding the intersecting point. So yeah, any more questions? So let's basically see how we can. What is the question? So basically, if you have questions, please find the other account of the mine so that I can see your the question on my screen. Yeah, so since we are running out of time, let's go into this. So what we are going to do is that from these two information, the radius information, which is the view dependent color information. So basically, you can see that this radius is basically the color information, right? Along the array for each of the point. And what does basically this density mean? So I said that this is kind of the density information. But basically, precisely, this is the information about like, how likely the ray will stop at the point. So this is kind of the probability, the term, which should not be the negative, which is giving the information like how likely the point will stop at the point. Does it make sense? And then what's the meaning of this T? This T is basically the term which is about the transparency, which also means that how likely the ray will not stop until the ray reaches at the point. Does it make sense? So the ray will basically travel along this direction. So if you see each of the point here, we're gonna first basically calculate sort of kind of the probability in terms of how likely the ray will basically pass through along this direction without making any kind of the some interactions with the particle. Without stopping along this direction, how likely the ray will basically fly along into until this point. That's the T. And basically the sigma, which is the quantity that we are predicting within the neural net, is basically the probability. So once basically the ray basically goes until this point without making any kind of the interactions, how likely the ray will stop at exactly this point. So that's basically the quantity that we are predicting, which is kind of the density, which is precisely opacity, or the extinction of the coefficients that we are going to see on the next slide, right? And also, obviously, the thing is that we should be able to compute this transparency based on the opacity that we are getting. So depending on the opacity, the values that we are getting until this point, we can calculate this transparency. So that's what we are going to do. We are not basically predicting these two quantities independently, but based on basically the opacity term, which is giving the information like how likely the ray will stop at each of the points, we're going to also compute how likely the ray will not stop until it reaches at this point. So here, all the thing is that basically how we can compute this transparency based on the opacity information. And as you can see, actually the transparency is defined like this. And if we briefly see like why it is defined like this, basically you can see that. So this is basically the basic idea behind all this kind of equation. So what we can basically see here is that we can assume that we are shooting a ray, which is kind of the very thin cylinder, right? we can assume that the ray in the 3D space is kind of like very thin cylinder in this 3D space. And each of the points in this 3D space will be basically taking some kind of also the slice of each of the cylinder, right? So you are shooting a ray like this, which is the thin cylinder in this 3D space. And taking a point is basically taking a slice of this cylinder, right? So basically here, this is basically kind of the slice of the cylinder where basically we're going to have some kind of the particles. So we are now seeing all these 3D objects as kind of a set of the particles in the 3D space, right? So we are basically having a set of the particles. In this space, we are basically getting the information about like the particle density. So if you multiply this density by basically the size of the volume of this slice, you get basically the exact number of the particles, right? So this is the multiplication of the density of the particles and the volume of the slice. And what the A basically means that basically the projection, the area. So basically when you see all the particles, when you assume that all the particles are basically the sphere like this, then basically this area will be some kind of the projected area of each of the particle. Then what we can see is that when you multiply this projected area with the number of the particles and divide this by the projection area of this kind of a slice, this area, this will be basically the ratio or like how likely the ray will stop at the point, right? So this is basically the area of some kind of the occluded region divided by the whole region of the slice of the cylinder. Make sense? Any questions? So I keep seeing that someone is like sending a message to my iPad. What is it meant by the project area? Well, I mean, so we are seeing all the particles through this direction, right? Okay. This direction. So the projection, the area is basically the projection of like this sphere. When you basically assume that all the particles are basically sphere, the projection of like this sphere along this direction. Then basically the projection, the area will be this area, right? And the projection area of all the slice will be this area, right? So if you multiply the projection area of each of the particle with the number of the particles and divide this by the area, the projection area of the whole the slice of the cylinder, that will be basically the ratio of the occlusion. How likely the ray will basically stop at this point. So what we can basically see is that this is also multiplied by the delta t here. So we can see that this is basically the quantity that we are saying as kind of the opacity, the extinction coefficients, basically how likely the ray will stop the point. So please send the message to the my account. I'm having the two accounts now, and I cannot see the chat to this account. So the cylinder is a projection of the sphere A. No. So what I'm saying is that, so we are having this cylinder. Okay. We are shooting the ray through this cylinder. And in this cylinder, basically, we are having all these small particles like this, right? So for all these kind of like these small particles, basically, it's all the matter of like how likely the ray will stop at this point, right? At this specific slice. And basically, what we want to do is that we basically want to count the number of all the particles here and see basically the projection the area along this direction, the view direction. And if you multiply the projection the area of each of the particle with the number of the particles, that will be basically the whole region of the basically that will be basically occluding the ray to pass through this slice. So we can basically divide the whole region of basically making some intersection with the ray, with the particles, divide by basically all the area of this slice here. Make sense? What is the difference of the meaning between the transmittance and the density? So that's basically what I'm going to explain. So I'm going to explain the meaning of the relationship between the density and the transmittance. So what I'm basically going to say is that we can basically calculate. No, we can basically get the quantity of like how likely the ray will stop at this slice. So this is the quantity that we are saying is kind of sorry, not this one. Basically this quantity. So this is the quantity about like how the ray will likely stop at each of the point along the ray. So that's basically the density that we are saying. So precisely that's basically the opacity, the information. And based on that, actually we can compute the transparency. So the transparency can be basically computed. So the transparency after the times of the t plus the delta t can be computed basically by multiplying these two terms. So the transparency basically means that like how likely the ray will not making any kind of the interactions with the particles until this point, right? And the probability for this can be computed as kind of the probability that the ray does not stop until the time t multiplied by basically this. So basically, this is the probability of like how likely the ray will basically make some kind of the interactions with the particles. And 1 minus the probability with the basically the probability like how likely the ray will not make any kind of the interaction at this slice, this specific slice. So basically what we can see is that if the ray does not make any kind of interaction until this point, and also does not make any kind of interactions at this slice, that's kind of the probability, like how likely the ray will not stop until the point of the t plus delta t, right? Yes, now we are assuming that all the particles to have the same A, simplifying the kind of the things, right? So basically, we can see that now the transparency term can be calculated like this. So if we basically multiply these two terms, the transparency until the time t, and the probability that the ray will not make any interactions at this slice, if we multiply these two terms, that will be basically transparency at the t plus delta t. So this is basically, you can see that this is basically the ODE formulation. Basically, we are having the equation like this. So if you basically rewrite all the things, what we're gonna get is basically that dt is the same as my iPad some noise. T times d delta t. So in this equation, basically we involve the function of the transparency here, and also is the first derivative as well, right? So this is basically the ODE formulation. So if you take some other math courses to solve all this ODE formulation, you can see that actually the solution of this ODE formulation with the initial constraint that the T0 is 1, then you're gonna get this kind of formulation, right? So do you see like why the T0 should be 1? Because there should be obviously no intersections at the very initial point, right? So we are starting from the 1 of the transparency. Obviously, the probability that the ray should not stop at the initial point should be 1, right? No interactions at the very beginning. And then we are basically getting this kind of the formulation. So what we can see is that if you basically plot this basically the formulation with some kind of the non-negativity values of the density here, then obviously it's basically accumulating this quantity with integral over until the time t. So basically, if we see this integral, this will be basically obviously decrease function because we are adding some like all the non-negative values, right? And if we take the exponential of the minus of this term, then we're gonna see the non-increasing function as the transparency, which makes sense, right? As you go further along the ray, the probability or like how likely the ray will stop, we will not stop until that point, we should not be increasing, right? As you go further, the probability of like how likely the ray can basically fly until that point without making any kind of the the interaction should not be increasing, but it can be decreasing. So which can be like physically making more sense. In the previous the idea, the visibility of the voxels can be random, right? So we can see some kind of cases that the closer the voxels have the lower the visibility, while the farther the voxels have the higher the visibility, which can basically break some physical rules. But this is like physically making more sense in terms of that the transparency is becoming some kind of the non-increasing function. So it can only decreasing along the way as we go far. Does it make sense? Any questions on this? So this is the whole idea. The question: are these particles mean the particles located on the surface or the objects? Once inside object. So here basically there's nothing about the surface. Everything is just the volume. So that's why we consider some particles. So we are assuming that there are some kind of some volumes, like some kind of smoke or the fluid in the 3D space. And we want to render this kind of set of the particles into the 2D plane. What was the previous question? Can you just like repeat the same question? So basically, you guys are like sending me the messages into all the different accounts, so I cannot. Yeah, actually, I think I assumed I answered the question. All the particles seem to be having the same A. Yes, the answer for that is yes. Like we are assuming that simplifying all the things in terms of every particle is basically the same with the same sphere with the same the project area. I mean, transmittance and the transparency, these are the same thing. Any other questions? Yeah, so if you have any other further questions, actually, please do not post the questions during the lectures on the Slack, because it's also very hard for me to basically track both the Zoom and the Slack. So yeah, but in any case, we are running out of time, so I think we need to just wrap up. So if you have like any further questions after the lecture, please post the questions on the questions channel in the Slack, and then I guess we won't have time to basically go further into all the details from the NERV. So but basically, as you know, the assignment 2 is basically implementing the NERV. So you will basically need to get all the information, like all the basically the ideas, basically how you basically need to basically implement all the things. So please check out all the details in the slides. You can also find all the slides in our course webpage. And if you also have any questions on the NERV, please put the questions after the lecture on the questions channel. And yeah, so as I also mentioned in the last time, we are not gonna have the lectures next week, and also in the week after the next week, we are not gonna have the lecture on the Monday because it's the Hangul, the holiday, and we're gonna have the guest lecture on the Tuesday at the 4 p.m. So please check out the guest lecture schedule. And also we're gonna have the meet of week. So we are not gonna have the lectures in the meet of week. And the first lecture after the meet of week will be basically the project pitch. So please check out the information about the project pitch in our course webpage. Is we're gonna see all the project ideas like all together in the first lecture after the meet of week. We're gonna resume some of the discussions about the NERV and also some kind of the next versions of the NERV after that. And then we're gonna start to discuss some kind of the ideas about the 3D generated models. Actually, I also prepare some slides for some kind of the tips for the project. So I'm going to also just post all the information on our Slack, so that you can also check that out when you prepare all of the projects. Any questions? Yeah, so if you have any questions after the lecture, please post the questions on the question channel in the Slack. So we're gonna also be able to discuss on the Slack after that. So I will see you in the week after the next week in the guest lecture. Okay. Thank you. Bye.